Hello, my name is Dr. Tamal Pramanik. I am an assistant professor of NIT Calicut at Department of Mathematics. So, today in this session, I will present finite element space and basis functions. So, what is finite element method? So, finite element method is a numerical method for solving various PDEs and ODEs and mathematical models in science and engineering and in mathematical physics. So, it is a very useful numerical tool for solving ordinary differential equations as well as partial differential equations. So, what it does? It does basically it reduces a ODE and PDE system to a system of algebraic equations which solves this system of algebraic equations in a traditional way of linear algebra techniques. So, what is the basic idea behind the finite element method? So, the basic idea of finite element method is subdivides a larger domain to a smaller and simpler domain. Each part is called the finite elements. So, each simpler part we solve our model problem. Then after solving each simpler part, we assemble the system of equations and imposing the continuity conditions, then we get a entire problem models, and that models is represents the entire problem and which solves the our given problem. So, what is the motivation behind the finite element method? So, finite element method basically subdivides a domain and we get the accurate representation of any complex geometry, and then it represents the total solution in a easier way, and we can capture also the local effects. So, here are some examples of finite elements in 1D. If we see, so for spring, truss, beam and pipes, we get the finite elements in 1D as an interval. Similarly, in membrane, in plate and cell, we get the finite element in a triangular form. Similarly, in 3D fields, in temperature, displacement, stress and flow velocity, we get the finite element in a tetrahedron form. So, I will show how the finite element space and finite element formulation construct for a given model problem. In this case, we have considered a horizontal elastic bar. Okay. So, suppose the horizontal elastic bar is given in the interval I is 0 to 1 and ux is denote the displacement of a bar at any point x in that interval, and ax is the modulus elasticity with some restriction that between 0 to 1, when x is lies between 0 to 1, ax is greater than 0 and fx is the given load function. So, with these conditions we will get the model boundary value problem like this: minus ax u dash x whole dash equal to fx for 0 to 1 and u0 and u1 is 0. So, this dash is denotes the derivative. So, 1 dash is denote the first derivatives, okay, and the boundary conditions u0 and u1 is 0. So, clearly this represents a Poisson type modeling for the horizontal elastic bar. So, next we introduce the L2 based Sobolev space, which is 801. So, what is 801 basically? 801 containing all the functions which is square integrable in the given interval. So, that means 0 to 1 Vx square plus V dash x square dx is less than infinity. And what is the notation 0? So, that 80 means that B0 and V1 is 0, basically boundary it is 0. So, by constructing this space we can write our variational formulation for this 1D problem, which is called also weak formulation. So, what it says? It says that first multiply by a test function Vx both side of the given problem. First we multiply by a test function Vx which is belonging to 801. So, after multiplying both side we will integrate in 0 to 1 and then we will do integration by parts. So after integration by parts, we will get the resulting equation like this. Then we will impose after integration by parts, we will impose the boundary conditions V0 and V1 equal to 0. So with imposing the boundary condition, we can clearly see that V0 and V1 is 0. So this first term will get removed. So remaining terms will be there. So finally the resulting equation becomes like this. So this is our weak formulation or variational formulation. So next we do the triangulation part. So triangulation is in the whole interval 0 1, we will discretize by taking some points which each equal length, suppose hk. So for a ik interval, we will take the distance hk from xk to xk plus 1, okay, and total we are taking m plus 1 number of points in the given interval. Okay. So th is denoting the triangulation which is 0 equal to x naught less than x1 up to xm plus 1 which is equal to 1, and ik is a kth interval xk minus 1 to xk, and hk is the mesh size which is xk minus 1. So with this formulation we construct the finite element space. So what is finite element space? It is denoted by Vh0. So what is Vh0? Vh0 is containing all the functions which functions are continuous in the interval. So C I P1k is denote basically all the continuous and piecewise linear functions in the triangulation Th. So that means Vh0 finite element space is containing all such functions such that which is continuous in the whole interval and which is linear in the kth interval. So in each part it is linear, and also with this 0 condition, with this 0 notation, we denote that V0 and V1 is 0. That means it is satisfying the boundary condition. So clearly Vh0 is a finite dimensional subspace of H01. So finally we can write the finite element formulation. So it says that UH from the weak form, we can write the finite element formulation which is for UH belong to VH naught such that integration 0 to 1 Ax UH dash x VH dash x dx equal to integral 0 to 1 Fx VHx dx. So for all VH belongs to VH naught. So today we have learned how to construct finite element space for a 1D problem, suppose horizontal elastic bar. So for a 1D Poisson type problem, how to construct finite element problem and how to write the finite element formulation by weak form. So in this last we will see that how to construct the basis functions for 1D. So suppose we consider any interval which is distance hk and then hk. So we consider xj minus 1 to xj plus 1. So at the point xj we construct the basis function as phi j. So phi j taking the value at the point xj is 1, and remaining at xj minus 1 and xj plus 1 it takes the value 0. So this way if we continue, so in the whole 0 1 interval, so we will get like phi naught, phi 1, phi j, phi n plus 1. So all the basis functions we will get. So in these sessions basically we see that how to construct finite element space, how to write finite element formulation for a model problem, and how to construct a basis functions for a model problem. So in the next session we will discuss some how to solving procedure, that finite element formulation, how to solve this equation. So next session we can discuss. Thank you.